Okay, let's see. It looks like we're recording. Everything's good. Okay, real quick announcement before I get into the math. I'm not wearing my sling. I got away with it with my morning class. Apparently, if I lean over and support my elbow on the table, then I can actually use my right hand, which really helps. Right? So anyway, fingers crossed that it'll work again this afternoon. Okay, so here's where we were last time. We were looking at this second special case. We had already entertained the idea of what happens when you have just a single input variable, and what happens is that this matrix over here only has a single column, which means you can think of this as being a velocity vector. Right? Okay, so we're entertaining now this idea of what if there is also only a single eventual output variable. And in that case, that means that the what you might call the second function of the two that you're composing has only a single row. And basically what it means then is that the computation of the composition derivative, right, the derivative of that composition, well, single row, single column, it's just a regular old, plain old Calc 1 derivative, right? Rate of change of the output with respect to the output. So the other thing that you might say is kind of convenient about this is that this idea of matrix multiplying a single row matrix times a single vector, I mean, just in terms of how you compute it, it's pretty literally a dot product, right? And so I can sort of reimagine matrix multiplication with a single row matrix as being effectively equivalent to dot product with the corresponding vector. And of course, that corresponding vector is just the gradient of the function. So you, in some sense, don't even really have to bring up matrices in a case like this where there's single number in, single number out, because the gradient vector, and just use dot product with the gradient vector. So not that it really matters much, right? I mean, if you wanted to do this with a derivative matrix, that's perfectly fine, but you have the option like this. Okay, so easy example, and again, I don't want to spend too much time on this because it's just literally what we saw on the previous page there. But the idea is that if you have a given velocity and you're keeping track of a real valued function, namely temperature in this case, then here you go. In order to find the derivative of the eventual output, single variable, right, original output temperature, with respect to your original input variable, which, since we're talking about motion, is time, right? Position as a function of time. That derivative, again, we compute with dot product with the gradient vector. Right? So you take the function that you're given, the function that you're trying to keep track of the rate of change of, compute its gradient, which you see in that process right there. Take the appropriate partials, plug in the point that you're given, okay? And then dot that with the given velocity vector, which is dx dt. Okay. All right. Okay, so moving along. Okay, I'm going to give you all a different point of view on the chain. Oh, sorry, question.
Oh, yeah. How did you know to use dx dt as opposed to like dy dt again?
Oh, so I say dx dt here with the x being the position vector. So that has coordinates x, y, and z.
Okay.
So yeah, in fact, I can highlight it like this. That x vector is all of this right there.
Okay.
Yeah. Everybody happy? Okay, so different point of view on the chain rule. And real quick, a reminder, our original point of view on the chain rule back here is that it's a statement about derivative matrices. And in particular, derivative matrices just multiply. Because each one of these derivative matrices represents an action that you do to a velocity, pretty much. And multiplying by one matrix and then subsequently multiplying by a second matrix altogether, what have you done? Altogether, what have you multiplied by? Well, you've multiplied by the product of those two matrices. Right? It's just sort of the associative property of matrix multiplication, roughly. Okay. So, statement about vector-valued multivariable functions and their derivative matrices. A very vector and matrix point of view on things. Sometimes that's a bigger tool than you need. Sometimes you're actually only interested in maybe one of the variables, or a partial of one of the variables with respect to one of the input variables, something like that. More of a sort of a coordinate point of view on things. So here's the scenario I want to consider. Suppose we have a function giving the y variables as functions of the x variables. You can write down the derivative matrix as a bunch of partials of y sub whatever with respect to x sub whatever, in the usual way. Then we compose that with this function that computes the z variables as functions of the y variables. And again, you can talk about its derivative matrix. And again, it's the partials of the z variables with respect to the y variables. Okay. All right. Now, all together, then, the composition is going to compute the z's as functions of the x's, right? So this sort of smashing them together, all together, the original input variables determining the eventual output variables. And you can talk about its derivative matrix. And, of course, what we have here is just a statement of the chain rule. The chain rule says that the derivative of the composition is the product of the individual derivatives, matrix point of view. What we're going to do now is, like I suggested, we're going to entertain the question of what if I only actually care about one specific partial derivative? I don't need to know all the others. I just want to know that one specific partial derivative. And how would I compute that? Well, I mean, we know how to compute an element of a product matrix. It's the corresponding row of the left matrix, dot the corresponding column of the right matrix, and you kind of, multiply and add the usual dot product way. So altogether then, that one specific partial derivative we're interested in is, well, you can see these blue factors there and the green factors here, and dot, dot, dot in between. And there you go. There's your one single formula. And what's nice about this formula is it allows you to compute the one partial derivative you're interested in without having to compute all of the other elements that you might not be. Right? You just don't have any particular need for. Okay, so this is a nice formula to have on hand, and we're going to talk about some different points of view on this formula going forward here. Okay. All right, so first thing I want to talk about is the notation, and it is a little unfortunate, but there is a temptation for students to look at this right here and kind of stop right at that point, ignore everything else, because they figure, doesn't this cancel with that? Can't I just cancel the partial y1s? And you see the temptation, right? What we have here is a shortcoming of the notation. It's a little frustrating. I don't have a good counterproposal for better notation. It's a hard problem in a scenario like this. But what you need to recognize is that you just can't do this. Very importantly, even though this looks like a fraction, yeah, it's really not. So please don't think of this as a standard fraction of independently well-defined independent things. It is not. So it's a nasty little problem, and you just have to sort of restrain yourself from that natural instinct. Now let me try to persuade you why this and this are different. And roughly speaking, the story, the explanation is they're part of different stories, completely different scenarios. Right? And imagine you're doing a homework set, and in question number 7, there's a reference to a variable x. Right? And then way back at the end of the same homework set, question number 42 also has a variable x in it. Well, they're totally unrelated, right? The x from number 7 has nothing to do with the x from number 42 that happen to have the same name, but they're talking about totally different situations. So that's what's happening here, believe it or not. Now, I'm going to skip over to the next page here just because I want to use the diagram. So for the moment, let me scratch out all of this. We'll come back and give our attention to this in a few minutes, but for the moment, I just want to make use of this diagram here. So let's talk about this partial y1 right there. What's the story that this is part of? All right, well, let's keep in mind we're trying to keep track of how much y1 changes, specifically, though, as xj changes, but furthermore, this being a partial derivative, only xj changes. Right? All of the other x variables are constant. Okay, so I can represent that on my, diagram here as follows. So xj is changing, and let's see here, y1, I did in green. I want to know how much y1 changes as xj changes, again with the understanding that the rest of these variables are all constants. Cool. By the way, presumably, right, if all these other variables are constants and xj is changing, what else is going to happen? Well, as xj changes, y2 is going to change, y3 is going to change. All these other y variables, they all depend on xj2, so they're all going to be changing. So this is the scenario that's happening when we are considering the partial of y1 with respect to xj. And yeah, I suppose how much y1 is changing is a part of that story. Sure. Okay. All right, now let's go back over to here. What's going on with this other story? This other story here. We're keeping track of how much zi changes when y1 changes. But now again, this is a partial derivative. Stand over here where I can point. This is a partial derivative with respect to y1. In a partial derivative, we have to treat all of the other variables, in this case all of the other y variables, they have to be constants. Okay, back to the diagram. So we're keeping track of how much zi. How much does zi change as y1 changes? Okay, fine, y1 was changing. But wait a second, in this story, all of these other variables are constants. They're not allowed to change. So that's a problem, right? We can't say this is the same scenario because in one scenario these other y variables are changing. In this other scenario, they are not allowed to change. They're just different stories. Completely different scenarios. So you can't compare. It's an apples and oranges thing to compare those partial y1s to each other. So I hope that makes sense. Yeah.
You gave kind of a more intuitive explanation of why, like I accept your argument, given that I know that they're changing or not changing, but why? Yeah. How did you figure out that they're not changing or changing?
By looking at the definition of what we're talking about. So when we say partial zi with respect to y1, right, the idea then is that zi is a function of a list of variables. In this case, it's y1 through yn, or m, y1 through ym, right? And partial derivative says all those input variables have to be held constant, except for the one that you're taking the partial with respect to. That's just the definition of a partial derivative. Does that make sense?
Yeah.
Yeah. So, So again, each one of them in some sense kind of represents how much y changes, y1 changes in a certain scenario, but they're different scenarios. Yeah. Is everybody happy? Okay. All right. So so don't make the mistake of thinking that you can cancel these. It just absolutely doesn't make any sense. Now, aside from the fact that it is bad reasoning, it's also going to obviously give you a wrong answer, because if you could cancel these, then your equation should have ended right there. Right? After all, if you could cancel, then that cancels with that. Does that make sense to everybody? Okay. All right. And of course, all of these other terms actually do have to be there, and they are important. Okay, moving along. Okay, so back to this diagram. We're going to look at this equation that we just wrote down, and again, we got this out of the matrix equation, right? And I'm going to try to come up with a way of thinking about this that doesn't involve matrices at all. Again, the goal here is to try to have a streamlined, more convenient way of getting to a result. So I think the following works really well. We are interested in the partial of zi. There it is in our diagram. With respect to xj, there it is in our diagram. And I point out that if xj changes, then all of these other y variables are going to be changing, because xj is one of their inputs, so each one of those y's is going to start changing. Is that cool? Right. Okay, so let's think about these one at a time. What happens when as xj changes, that causes y1 to change? Well, xj changes by a certain amount, y1 changes by a certain amount. What's the proportion between those? Said differently, what is the factor that I multiply by the change in xj to get the change in y1? And that's a partial derivative. That's kind of that's one of the primary interpretations, I'll say, of partial derivative. It's what you multiply by this input change to get that output change. So notice this factor right here corresponds then to the factor of how much the change magnifies as it propagates along that arrow. Okay, and then what happens to it? Well, the next thing that happens, however much y1 changes, that's going to cause a change in zi. Now, I emphasize here, I'm talking about y1 changing and only y1 changing. Yeah, sure, that y2, y3, etc., they're changing as well. We'll get to them later, right? But just the mere changing of y1 by itself contributes somewhat to how much zi is changing. And again, there's a factor. A change in y1 contributes to a change in zi. The change in zi is some factor greater than the change in y1, and the partial derivative is what determines how much this change magnifies to become that change. And so there's kind of along this path, this top path here, this original change in xj gets magnified by a factor there, it gets magnified by a factor here, altogether it gets magnified by the product of those two factors. Does that make sense to everybody? Yeah?
I guess another argument you could make to justify not canceling the partial y's is that y changes by a different factor in both scenarios.
Yeah, sure. I hear what you're saying. Now, if someone wanted to make it work, right, they could say, well, I'm going to keep, each one of these is a factor that you multiply by whatever the change is, and they can say, well, I'm just going to define partial y1 in each one of these cases to be the same, right? So the problem is really that it's really this other business about them being part of different scenarios. Does that make sense? I know it's a subtle It's a subtle point, yeah. And there was another hand, yeah.
So did you say that the change in ZI has to be greater than the change in Y?
No, it gets multiplied by a factor. That factor
Okay.
could be less than 1, could be greater than 1. No comment on that.
Okay.
Yeah. Could be negative. Yeah. All right. Okay, so the idea then is that each one of these paths, such as, for example, this path right there, each path represents a term in this formula. Right? And then I can do likewise for the other paths. Now there's, several other paths along there, and then I can end with, let's look at this last path. That last path corresponds to this term. And again, you can break it down into sort of steps. First, we have the partial of ym with respect to xj. There's that. And then we have the partial of zi with respect to ym. And there's that. Right, so each path corresponds to a term. And the clever observation, I think, is that not only does each path correspond to a term, but also each path corresponds to one of these variables that we call intermediate variables. It's one of the variables that's kind of in between. It's not one of the original inputs, and it's not one of the eventual outputs. It's one of these in-between variables, and each path that goes from xj to zi has to go through exactly one of these intermediate variables. So instead of thinking in terms of paths contributing terms, you can think of it as each variable contributes a term, each intermediate variable contributes a term, like that. And notice they line up pretty conveniently. The y1 variable contributes the y1 term that has the y1s in it that you're going to have that temptation to want to cancel, even though of course you can't. How's that strike you? Is everybody okay with that? All right. It's a very convenient point of view. Notice no matrices were necessary in making that case. And now let's see how we would use that in practice. Here's an example. I've got originally a function that turns some x inputs into some y outputs. That's the first function in my composition. Then I have, subsequent to that, I have a function that treats the y's as inputs and then produces z's as outputs. There's that second function in the composition. Right, and notice the question then is to compute the partial of z2 with respect to x2. And as you see from where those variables are in this little diagram, that's a partial derivative of the composition. Everybody on board so far? Setup? Okay, so great. With that setup being what it is, how many intermediate variables do we have? Whoops. Here, let me leave that right there. How many intermediate variables do we have? Well, we have 2 intermediate variables. The first intermediate variable gives us the first term. The second intermediate variable gives us the second term. Again, notice each one of these terms, like let's look at the second one here. This is the y2 term, and you see the partial y2s that, again, you kind of have this urge, you have to resist to want to cancel those. Everybody all right? All right, and at this point, of course, it's a matter of just cranking out a couple of partial derivatives. I'm going to mostly leave this to y'all, but notice some of this you can totally do on your own. Let's see here. Let's look at this one right here. Partial of y2 with respect to x2. Well, okay, let's see here. y2, there it is, y2, it's that function right there. partial derivative of this thing with respect to x2 is just x1 squared, as you see we computed here. Everybody good? Okay, so saved us a bunch of trouble. I didn't have to write down a bunch of derivative matrices. Right? Nice. Okay. I would like to comment here. You'll notice the very first thing that I did is I took the algebra in the statement of the question and I used that to produce this diagram. Right? I think the diagram is invaluable in helping you keep track of what's a function of what and which variables are where and which ones are in between which other ones. It otherwise can be very confusing. Right? So I think it's really, really nice to create your diagram and then let that be your guide in deciding, well, what am I taking the partial of what with respect to what, which are where in the diagram, and thus where are my intermediate variables. Yeah.
So how did you decide to draw like the y1, y2 between x2 and z2?
Yeah, sure.
Like if it's asking for x1, z1, would you draw them like connected to x1 and z1?
Oh yeah, I mean, so there's a bunch of arrows here that I didn't draw. I just didn't want my picture to get all sort of messy and stuff. But there's also let's see here. There's all of that, and it's just most of those, the ones that I have in purple there, just aren't relevant to what I actually needed.
Okay.
Yep. Yeah. Everybody good? Okay. Okay, so draw your diagram. It's next to essential to be able to make good sense out of what you're doing. Now, there is a nasty situation that you can find yourself in. It's a confusion of variables. It's ultimately the problem. I'm going to start off with a single variable example. This is going to be a lot of rewind really far back to when you were learning the chain rule back in Calc 1, which is again long ago. For the purposes of making it explicit and obvious how big of a problem this would be if you're not careful with it. But again, this is all Calc 1, so I hope this part's easy. A couple of functions, no problem. Right? F of x is x squared. Fine. G of x is x cubed. Not a thing wrong with that. But if I am supposed to compose them, there is potential to mess this up as follows. Notice if you're a little bit too careless and sloppy with how you write down the chain rule, and I do like how it rolls off the tongue, that the derivative of a composition is the product of the individual derivatives. See, I wrote that down. And then I just kind of say, all right, well, look, the derivative of this g function, derivative of x cubed is 3x squared. And the derivative of the f function, derivative of x squared, is 2x. And you get a wrong answer, right? You get 6x cubed. We know that's wrong. Because we know the answer is 6x to the fifth. Because we can literally compose these functions and take the derivative pretty easily. So that did not go correctly. What I guess I kind of sort of should have done is to be more careful in how I write g prime. Specifically, g prime has to be evaluated at f of x, not at x. And I hope you all remember this from Calc 1 long ago. And in particular then, with the idea being that g is really the cubing function, whatever it is you put into it, you're cubing it. The derivative of the cubing function is 3 times the squaring function, you might say. And if I'm supposed to, as the formula says, plug in f of x into that, f of x, of course, is x squared. And you see, I should have put an x squared in there, not just an x. Right? Flashbacks to high school calculus. Okay. And that gets me the right answer, and that's nice. But I got to tell you, I'm still not happy with this. I think that even this leaves something to be desired, because it's pretty confusing to not be able to just write down the algebra, to have to think of G as being a function without saying the name of the variable that I'm plugging into it, because I'm plugging in f of x instead of x as it's written. That's just weird and confusing. So look how much better this third option is. The much better third option. Let's just recognize that if I am going to take this function f and compose it with the function g, then whatever comes out of the f function, that's what I'm going to be plugging into g. I should probably write g in terms of that variable in the first place. So this right here, the fact that I'm calling the output from f y, suggests to me that I should be rewriting g to be a function of the dummy variable y, not x. And as such, you'll see here, here's that same function. G is still the cubing function, right? But I've written it as g of y equals y cubed instead of g of x equals x cubed. And now there's no confusion of variables, right? I've got distinct names for the original input, the intermediate, and the eventual output, all differently named, no confusion. And then you can be as casual as you want to be when you start writing down the chain rule. And look again, just to prove that I can. Look how casual I was again with the statement of the chain rule: derivative of the compositions, the product of the derivatives, right? Totally careless about what's being evaluated where. And now we just write down the derivatives. Let's see here, to find g prime. Well, I'm just going to take the derivative of y cubed, 3y squared, nothing to it. And now let's take the derivative of f. Well, I'm going to take this x squared and just take the derivative, 2x. Cool. And altogether then, our derivative ends up being, let's see here, this thing, 6y squared x. Okay. I can't quite stop there, because after all, the composition that I'm interested in, the composition is a function of x. Its derivative should be written, therefore, as a function of x. So I need to figure out how to rewrite my answer in orange. I've got to figure out how to rewrite that only in terms of x. So I need to plug in for what y is. And, of course, it says right here, y being, after all, the output from the f function, y. Plug that in. Y is just x squared, and we get the answer that we know we were supposed to get in the first place, namely 6x to the fifth. So I like this much better. No confusion of variables. The notation that you choose does the bookkeeping for you, right? Let your notation do your work for you. Don't trust yourself to keep it all in your head. Much safer that way. Everybody happy? Okay. All right, so now why did I spend a bunch of time on this single variable business? And the answer is because the exact same phenomenon happens in a multivariable setting. So here you go. Here's a question that you could encounter. A couple of multivariable functions. Not a thing wrong with either of them. Perfectly fine. F and G, both written in terms of x and y, not a problem. Until you decide you want to compose them. Now, as soon as you decide you want to compose them, G is now going to be coming after F. So what comes out of F is going to be what goes into G. Right? Well, let's start thinking carefully about what we're going to name what. And what I like to do here is leave things as they are until I have a reason not to. So I was given f as a function of x and y, so we'll leave it like that. What name am I going to give to these output values? Notice I can't call these outputs x and y. Well, of course not. X and y are the inputs. it would be ridiculous to call them also, the outputs also x and y. There's obvious confusion of variables. Right? So I give the name of the outputs, give these outputs a new name. We'll call them u and v. Okay. And if I'm going to compose, that means that, well, what came out of F had better be what goes in to G, and that means right here that I should rewrite G in terms of U and V. Just to avoid confusion of variables and to make everything sort of fit the way it's supposed to. Okay. Yeah?
Do you know whether notationally that they have problems like this, they're written like that confusing? Because I see what you're saying.
Yeah, sure.
That top coordinate is supposed to represent X, the bottom is supposed to represent Y, but it's still in terms of like...
Yeah, so you're wondering like why would any context arise where two functions that you're eventually going to want to compose are written in terms of the same variables?
Yeah.
And it's because you're not necessarily going to compose all the functions that you ever see, right? And sometimes you just have a couple of functions lying around, and they got to write them in terms of something, and you run out of alphabet letters eventually, right? And it just seems unnecessarily heavy-handed to rewrite everything, constantly rewriting things in terms of, and so sometimes perfectly innocently, you write functions with respect to the same input variables, and only subsequently do you decide, hey, you know what, I better compose these. And that's when the problem arises. So that's why I present this as something y'all have to be on the lookout for, right? Because you can't trust that circumstance will always guide you around these kinds of problems. Sometimes they appear kind of unexpectedly. And so you have to be on the lookout for them. All right, so same deal here. I've got to give the outputs from F a name. Arbitrarily, I'm going to call them U and V. Whatever names I give to the outputs from F, those had better be the inputs to G, which tells me I have to rewrite G like this. Now notice, that's the exact same G. These functions are identical functions. It's the same function, just written in terms of different dummy variables. They're just dummy variables. Does that make sense? Okay. Alrighty. And again, it's kind of all over but the shouting at this point. Now that we've got a clear diagram and we have our functions written in terms of an appropriate choice of unconfused variables, then, yeah, sure. Take the derivative matrix of each one. Derivative of the compositions, the product of the derivatives. You write that down. And just at the end, don't forget to plug in what you have. And in particular, for example, this U right here. What is that U? It's the first input variable to G. Fine. But it is that because it's also the first output variable from F. And so that means that U is x squared plus y squared. And then likewise, what's the deal with the this v here? How am I going to figure out what that v is? Well, v is the second input to G because it's the second output from F. And so that v is x squared minus y squared. Is that cool? And it's all over but the multiplying out these two matrices. So, multiply it out. Y'all know how to do that. Okay, so heads up on that. Nice little landmine to be careful with. Here is a kind of related sort of more general problem. It's common confusion. Actually, let me go back here for a second. So look at this example again. And recall, we were given two actual functions to be composed. These are two legitimate multivariable vector valued functions that I am literally composing. Look back, in fact, at our original scenario where we came up with the chain rule in the first place, right? It hinges on it being literally a composition of actual functions. Right? Now, we shorthand that as I did here, by drawing a diagram, right? So if you have two functions that you're composing, you can generate a diagram. It doesn't necessarily go the other way. If you have, by some unknown circumstances, found yourself looking at a diagram, it does not follow that that actually came from a composition of functions. It's not clear that the chain rule as we understand it applies at all unless there are actual functions that you're composing to make your diagram. And again, sometimes that just doesn't work. So here we have a good example and a bad example. Here's a diagram that actually is a composition of two functions, and you can see them. You can see that there's this function f, where the x's are the inputs and the y's are the outputs, and that's being composed with this function g, where the y's are the inputs and the z's are the outputs. And notice all of these conditions up here, these 3 bullet points that I've written down, everything works, right? There's no confusion of variables. For each of these functions, the inputs are independent. See, x1 and x2 are totally independent of each other. x1 is not a function of x2. x2 is not a function of x1, right? And last bullet point, the outputs from the first function are the inputs to the second function. So that diagram there actually is representing a composition of actual functions. Now let's look at the second one. I claim that this one isn't. This just doesn't follow the rules. Where are the two functions that are being composed here? You know what I mean? So for example, look at z1 here. What is z1 a function of? Well, it seems, right, z1 appears to be a function of kind of all 3 of these variables, x1, y1, and y2. But tragically, y1 is a function of x1, right? It doesn't make any sense. This is not a composition of two, acceptably defined functions. And so then, let me ask the related question. What does this mean? Partial of z1 with respect to x1. Tempting to say, all right, well, let's just follow the rules. The partial of z1, here's z1, and we'll take the partial with respect to x1. That means x1 is going to be a variable. That now being a partial derivative, that means y1 and y2 would have to be constant, but it can't be. If x1 is changing, check it out, y1 is a function of, among other things, x1. If x1's changing, y1 would be expected to be changing too. So this doesn't even make sense. Does everybody see what's gone terribly, terribly wrong here? Right? So again, the problem, the as I see it anyway, the problem is that we have a chain rule for composing multivariable functions. This is not a composition of multivariable functions. We do not have a chain rule to address this situation. Is that everybody on board? See the problem? Okay, so how do we deal when a circumstance like this comes up? And it actually does. Surprisingly often. Notice this example down here, and I'm going to walk you through the equations. Let's look at, it says here y1 is a function of x1 and x2, just as I have drawn there. And let's see here, y2 is a function of x1 and x2. Cool, just like I have drawn there. And let's see, we have z1 seems to be a function of x1 and y1 and y2. And z2 is a function of y1 and y2. So here is a set of equations. that you might find yourself dealing with at some point, a bunch of equations describing the relationships between various different variables, and you'd be forgiven for writing down a diagram that looks like this because that's what the equations say. Right? And again, you're going to want to be able to apply the chain rule up here, but you can't because this isn't a composition of functions. So we're up a creek. Yeah? There's a fix for this. The fix is to this diagram, I'm going to create a new variable sort of right there where that orange dot is, right? And I'm going to need to zoom out so we can get this all on the screen. Here we go. I'm going to put a new variable right there. Here it is. I'm going to call it x1 star. The idea is that x1 star is look, it's a placeholder. Its value is whatever the value of x1 is. It's not actually an independent thing. But because I create it and call it a new variable like that, now notice that my diagram all fits and everything makes sense. I have input variables over here, and I have intermediate variables now here, and then I have my eventual output variables there, and no problem. I have now literally a composition of two acceptable multivariable functions. And now I can apply the chain rule. Does that make sense to everybody? Yeah.
It says you might be able to fix problems. What are the situations where that wouldn't work?
Oh, yeah, that's a good question. I'll say that any situation where you can't fix it will definitely not come up in this class. I'm not prepared to have an explicit example of something where you can't fix it like this. So I'm going to punt on that question. It's a great question. I'll think about it and I'll get back to you.
Okay.
Yeah, but not anything you're going to have to worry about for Math219. Okay. All right. So now you do have to change things a little bit here in order to make this all make sense. Recalling, we have this equation right here that in the given that says z1 is a function of y1, y2, and x1. But it's not allowed to anymore. I now need z1 to be a function of x1 star and y1 and y2. So no problem. After all, x1 star is x1 by design. It's just a placeholder to allow my diagram to make sense. It's not actually any different from x1. And having done that, we now have altogether, let's see here, cleaning up my mess, we have 4 equations, there, 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 and there. And you can totally write down the chain rule. And so, for example, now let's look back up here. We failed up here to make sense out of partial of z1 with respect to x1. That didn't even make any sense. Down in our fixed situation, partial of z1 with respect to x1, no problem. We have 3 intermediate variables and thus 3 terms, and off you go. It's all good at this point. Everybody happy? Okay. All right. Okay, moving along. Oh, yeah, question.
So is the partial derivative of x1 over x1 just 1?
Yeah.
Okay.
Yeah. That's right. So just to be explicit on that, this partial derivative right here, don't forget they are literally, x1 star is literally x1, and so that partial derivative is literally 1, and thus that factor just kind of disappears. Yeah. Okay. All right. Okie dokie. So second derivatives. The key point that we're eventually going to get to is what I start with here. If you have a function of a given set of variables, I've made this observation before. If z is a function of x and y, so are its partials. Right? If z is a function of x and y, then zx for example, is a function of x and y also. Okay, so keeping that in mind, the method here for dealing with second partials is not a matter of writing down like a theorem or something. This is just a kind of a sort of an interpretation of how to make sense out of weird circumstances that arise. So I'm just going to dive into an example, show you what the weird circumstance is, and then show you how to deal with it. I'm going to show you the wrong way to deal with it, and then I'm going to show you the right way to deal with it. Okay, so here we go. Notice z is a function of x and y, thus that part of our diagram. R and theta are polar coordinates. Don't forget what that means. That means that x and y are functions of r and theta. And our goal is going to be to talk about partial derivatives of z with respect to r. So we're going to look at this composition and want to take partial derivative, actually two partial derivatives. That's going to be the sticky part. We'll get to that in a minute. But we have a composition of functions and therefore this diagram here. Is everybody with me before I go on? Okay. By the way, for whatever it's worth, this is a very standard classic first example of this kind of thing. And the reason is that it's also very natural. This kind of thing happens. And I have an awesome example I'm going to show you. It's going to end up being next time. There's no way I'll get to it today. But if you're doing physics, I could personally attest to, and I think as many of y'all are going to be engineers, y'all are going to be doing something pretty similar at some point along in there. It's very regularly the case that you find yourself with a function written in terms of x and y, but that you need to be able to think of in polar coordinates, and you need to be able to understand its derivatives with respect to polar coordinates. So this kind of thing, again, natural. This comes up regularly and routinely in real physical scenarios. Okay, so all that said, let's start with the regular, just single derivative partial of z with respect to r. This first part is pretty straightforward. We have two paths and therefore two terms. Right? Using our usual intermediate variables trick. Notice partial of x with respect to r is easy. That's just cosine theta. Right? And likewise, partial of y with respect to r, that's just sine theta. After all, x is our cosine theta, and y is our sine theta. Is that cool? Everybody with me? Okay. All right. Cool. Let's see here. Now, next, by the way, don't look at this part of the notes yet. We'll come to that in a minute. Just a distraction for the moment. How are we going to compute the requested second partial? Well, we're going to take the r partial of the r partial. Fine. The r partial is what we just got through computing. We'll just plug that in. Yeah. Now here's where we have to start being kind of careful. How am I going to make sense out of this whole thing? And it's very important at a time like this to be explicit on your diagram, at least to yourself, about what's going on, what variables are playing what roles. So notice we're taking a partial derivative with respect to button isn't. Oh, there we go. The partial derivative with respect to r. When you are taking a partial derivative, the other variables there in that same stage are constant. Right? So theta is a constant. While I'm doing this calculation down here, I get to treat theta as a constant. And beautifully, if theta is a constant, then cosine theta is a constant and sine theta is a constant. And when you have constants in a derivative expression, those constants just kind of factor out, right, in the usual way. And so there's that. Everybody good with that? Yeah?
Where's the R in that?
Where the what now?
Okay, where's the R? Are you taking the derivative with respect to R?
Yes.
Where is that located?
So, well, in the diagram, the R is here. I'm not really doing anything with the R right now. I'm just making the observation that the theta is being as theta is a constant, then cosine theta is a constant, and it factors out. I'm not sure if I answered the question.
I see. You kept the derivative.
Yeah. Right. Yeah. Okay. All right. Okay. So now, what do we do with this right here? Partial of zx with respect to r. So let's see here. Oh, you know what? I just ran out of time. Okay, so I'll tell you what. This will be a good place to start on Wednesday because this is where it gets starts to get a little tricky. So we'll pick up here on Wednesday. Y'all have a good rest of your Monday. See you later.